I'm Kyle Min from Intel Labs, and I'm going to present an effective method of learning long-term spatial-temporal graphs for active speaker detection. Active speaker detection, or ASD, is a multimodal task where the goal is to predict whether each person in the scene is speaking or not. Recently, researchers started to use the context information in multi-speaker scenarios for ASD. Many of the recent methods leverage the long-term relationships between the potential speakers. They consist of two stages. Stage 1 is a feature encoding stage for the audio-visual feature extraction, and Stage 2 is a context reasoning stage where its job is to model the long-term relationships between the speakers and their temporal patterns. We propose a new method based on spatial-temporal graphs named SPEL, which is capable of modeling extremely longer-term context information, and on top of this, has lower computation cost. SPEL converts a very long video into a graph structure, where each face region corresponds to a graph node, and the spatial and temporal relationships between the faces are captured by graph edges. After constructing the graph, SPEL uses GNNs to solve the problem of ASD as a binary node classification. Now I'll explain our proposed method of constructing the spatial-temporal graphs from a video. In SPEL, each face in a frame is used as a graph node. For the edges, there are two types. First, we connect all the nodes within a frame to encode the spatial relationships between different face regions. In addition, the nodes corresponding to each face identity are connected across the frames to encode their temporal dynamics. For this second type of edges, we found that using all three forward-backward undirected edges can boost the performance by embedding more detailed temporal information. After we construct such graphs from a video, we use GNNs to predict a binary label for each graph node to decide whether the corresponding face is speaking or not. Specifically, for each forward-backward undirected graph, 3 layers of GNN modules are used to aggregate the spatial-temporal information. The first layer is implemented by EdgeConf, which is known to be effective in modeling pairwise relational information. SageConf has a similar form, but it models an information from a single node, so it has fewer parameters. We discovered that placing EdgeConf first and placing SageConf in the next 2 layers provides better performance while using less number of parameters than other possible formulations. For the results, we first show that SPEL is effective in learning useful context information. All these methods in this table have multi-stage frameworks. Here, Stage 1 MAP is the detection performance when using only the feature encoding stage or Stage 1, so the difference between this and the final MAP can provide a good insight on the performance of the context reasoning modules. As you can see, SPEL outperforms all the other methods in terms of the context reasoning performance. In the table below, we compare the complexity of the context reasoning stage of SPEL with ASC and ASDNet. These methods have more than 10 times the parameters and the model size than ours, but ours provides more performance increase. Although the results of these two tables demonstrate that SPEL is effective, the final MAP is still about 1% lower than the leading state-of-the-art method. This is because recently proposed methods rely on complex architectures to improve the quality of the audio-visual features. For example, as we can see from the table on the right, TalkNet and ASDNet use 3D CNNs in the feature encoding stage, which require more parameters and computation cost. Instead of using complex 3D CNNs, we improved the performance of the feature encoding stage by using a technique called TSM that provides supplementary short-term temporal information without introducing any additional parameters nor computation cost. By using a 2D ResNet architecture augmented with TSM, we could improve the final performance a lot and achieved state-of-the-art performance. That concludes my presentation. Thank you for listening.